Welcome to this SiC Power Semiconductors Paralleling and Real Designs video. Here, you will understand the benefits of connecting SiC power MOSFETs in parallel. Get to know the key challenges of inter-chip oscillation in parallel SiC power MOSFETs. And be familiar with design measures to ensure the reliable operation of SiC power MOSFETs in parallel. Unlike power diodes or thyristors, modern MOS-gated power semiconductor devices, like IGBTs or MOSFETs, are usually made up to a certain chip size due to the production yield consideration. Therefore, to increase the overall current carrying capability and reduce power dissipation, power MOSFETs are often used in parallel connections. So, taking the comparison of the 1200 volt 25 ampere rated IGBT7S7 and the 40 milliohm M1H SiC MOSFET in a TO247 package as an example, we can see that both devices have a similar rated DC continuous current of around 40 amperes at the case temperature of 100 degrees Celsius. However, due to the strong positive temperature coefficient of its on-state voltage, the SiC MOSFET is widely used in the parallel connection. If only one device is used, the SiC MOSFET shows its significant benefit in the on-state losses when compared to the IGBT, especially in the low current range, or light load mode. Using two devices to further increase the current carrying capability of the end product, the on-state voltage of the solution based on the SiC MOSFET is reduced by a factor of 2, while for the solution based on the IGBT, the on-state voltage is only reduced by roughly 20%, due to the diffusion voltage of the collector side PN junction. So, what are the key challenges of parallel connections? When connecting two MOSFET chips in parallel, inter-chip oscillation can occur during the switching transient. Due to the ringing of the gate voltage signal, the load current may be periodically redistributed between the two parallel connected MOSFET switches and cause severe electromagnetic interference problems. In the worst-case scenario, the MOSFET chips can be permanently damaged due to overheating caused by the inter-chip oscillation. This oscillation tendency is influenced by the characteristics of the MOSFET chip and the parasitic capacitances and inductances in the circuit. Since this kind of inter-chip oscillation usually happens between the two parallel connected chips via the drain-to-gate capacitance, also known as CGD, or via the gate-to-source capacitance or CGS, the oscillation frequency is usually above 100 MHz. Due to the high impedance, this high-frequency oscillation signal does not pass into the gate drive circuit or the DC circuit. This means that a large external gate resistance cannot suppress this kind of oscillation. In fact, a large external gate resistance can make the problem even worse. SiC MOSFETs are prone to oscillation due to their high switching speed. It is necessary to carefully differentiate the inter-chip oscillation from the LC oscillation caused by the stray inductance L sigma and the output capacitance COSS. This LC oscillation also occurs during the switching transient, even though it's mainly due to the steep change of current and voltage. During the LC oscillation, the oscillation amplitude is always reducing with time since there are damping elements in the circuit. In comparison, the inter-chip oscillation is self-sustained due to the amplification function of the power semiconductor devices. The oscillation amplitude can increase or decrease depending on the operation point. Moreover, a power semiconductor chip with the transconductance GM can be modeled as a current source controlled by the gate voltage VGS. Therefore, the risk of inter-chip oscillation is not a unique problem for SiC MOSFETs. In fact, a similar observation was also reported for other power switches with similar amplification functions, such as the IGBT and the GaN-HEMT. Another characteristic used to distinguish inter-chip oscillations is the oscillation frequency. This frequency of the inter-chip oscillation is usually way above 100 MHz due to the small inductance and capacitance in the loop with several chips in parallel. However, LC oscillation has an oscillation frequency usually below 100 MHz due to the relatively large stray inductance L sigma and large output capacitance COSS when more than 10 SiC MOSFET chips are connected in parallel. Now, let's go deeper into the physics behind this problem. Due to the chip parameter difference or layout asymmetry, a certain initial disturbance signal V0 is always present in the system, especially during the switching transient. One important root cause could be the layout asymmetry, which causes transient current imbalance and potential differences between the gate of the parallel MOSFETs. This oscillation tendency is given by the MOSFET chip characteristics and the parasitic capacitances and inductances in the circuit. It can be modeled with the term delta for the damping factor or minus delta for the amplification factor. Omega in the equation describes the frequency of the oscillation. The problem of inter-chip oscillation given by V, or output voltage, becomes visible when an initial disturbance signal V0 is not equal to 0 and the amplification factor minus delta is positive, which gives a positive amplification of the disturbance signal, following an exponential function. The initial disturbance signal can be, for example, the potential difference between the gate potential of the two parallel connected MOSFET chips. Due to this potential difference, one displacement current would flow to discharge the MOSFET chip with higher gate potential and charge the MOSFET chip with lower gate potential. Due to the parasitic capacitance and inductance in the circuit, this current would be alternating periodically between the two parallel connected MOSFET chips. If the positive feedback in the system is too strong, this displacement current gets amplified, following an exponential function when alternating periodically between the two MOSFET chips. Note that the risk of inter-chip oscillation is usually higher when the MOSFET is in the linear mode. During the switching transient, the device will operate in the linear mode, crossing the area with instability risks for the paralleled chips. If an unnecessarily large external gate resistance is chosen, the MOSFET chip will stay too long in the unstable area, which allows for the disturbance signal to follow an exponential function until the oscillation signal is visible, eventually leading to the destruction of the MOSFET chip. When it comes to design measures, since the external RG is not within the oscillation loop, it is helpful to put it into the loop between the gate terminal of two parallel connected chips. This will enable a strong damping effect for the potential oscillation issue, without sacrificing the switching speed. In general, if unnecessary, a large external RG should be avoided to prevent a lengthy operation in the area with instability risks. Since the initial disturbance signal is caused by the chip parameter difference and layout asymmetry, to ensure a reliable operation, the MOSFET chips used in the parallel connection should be carefully chosen. This is because the risk of inter-chip oscillation can be reduced if the MOSFETs are well matched, particularly in terms of threshold voltage and gate charge. A proper gate drive is also critical for parallel MOSFETs. Thus, gate drivers capable of delivering adequate gate source voltage and current for all devices in parallel should be used. Last but not least, a symmetric layout is the key to reducing the initial disturbance signal. The source side inductance should be minimized, which is one of the most important impact factors for the oscillation tendency. In order to reduce the source side inductance, the power source terminals of the parallel MOSFET should be connected as close as possible. You are now at the end of this video about the SiC power semiconductors and real designs, paralleling. If you need additional information, please take a look at this page at Infineon.com. Thank you for watching.